A developer adds one tiny package. The package manager quietly downloads 5 more. Those packages bring their own dependencies. Within seconds, code from strangers is inside the application. The team may never read it, review it, or even know its name. That same utility can enter thousands of products through the same automated path. In 2021, Codecov disclosed that its widely used bash uploader had been altered without permission. The modified script reached users through normal development workflows. The delivery system itself had become the attack surface. If trusted tools can carry untrusted code, where does the product end and the supply chain begin? And how can a company secure software assembled from components, services, accounts, and machines it does not fully control? The answer starts with an uncomfortable fact: modern applications are not built alone. They are inherited. The software supply chain is everything required to turn source code into a product and deliver it to a user. It includes company code, open source libraries, the package manager that fetches them, the build system that combines them, the cloud service that hosts them, signing keys, and outside vendors. Think of it as a factory whose parts arrive digitally. An application may look like one product, but its behavior depends on many organizations and machines. Every handoff creates efficiency. Every handoff also creates trust. A library must be what it claims to be. A build server must produce what developers intended. A vendor update must arrive unchanged. If one link fails, downstream users can inherit the failure automatically. That is what makes software supply chain risk different from a bug isolated inside one company's code. The same trusted path can distribute one mistake, or one malicious change, to many customers at once. Log4 shell is an example of an accidental vulnerability with supply chain consequences. Apache's Log4j was a legitimate logging library. In December 2021, CV 2021-44228 was disclosed in versions from 2.0 beta 9 through 2.14.1. The package was not created as malware. The flaw sat deep inside Java systems, often through indirect dependencies. Organizations first had to discover where Log4j existed before they could patch it. SolarWinds showed a different failure. Attackers compromised the build and distribution process for Orion updates and inserted the Sunburst backdoor. Customers received the malicious component through a trusted update channel. The source of trust became the delivery mechanism. Codecov exposed another route. The company said an error in its Docker image creation process allowed an actor to obtain a credential used to modify its bash uploader. That script could run inside customer build environments, where secrets and tokens are often present. In 2024, malicious code was discovered in upstream XZ Utils tarballs beginning with version 5.6.0. The attempted backdoor was caught before broad adoption in stable Linux distributions, limiting its reach. A near miss is evidence of risk, not permission to inflate the impact. In 2021, 3 versions of the npm package ua-parser-js were published with malicious code after the package was hijacked. That was deliberate abuse of a trusted package identity. These incidents share a category, but not a cause. Patching a bug is not enough when the release process itself cannot be trusted. Most but it cannot settle the trust question. Dependency scanners compare package names and versions against databases of known vulnerabilities. They can identify a disclosed flaw quickly across many repositories. But known is the limiting word. A new vulnerability has no entry until someone finds, verifies, and publishes it. A malicious package may look harmless during static analysis and activate only during installation, a particular build, or a rare environment. A compromised build server can produce a bad binary from clean source, so scanning the repository may see nothing. A stolen signing key can make an untrusted release appear authentic. A scanner can also miss dependencies when manifests, generated files, containers, or vendor components are incomplete. Behavior is contextual. A network connection may be essential in one library and suspicious in another. Automated tools can rank risk, but they cannot reliably infer every developer's intent or every system's expected behavior. False positives create alert fatigue, false negatives create false confidence. Scanners are detection systems, not certificates of safety. They are strongest beside accurate inventories, human review, provenance, runtime monitoring, and a plan for revoking trust. Defending the supply chain means stacking controls so one failure does not decide everything. A software bill of materials creates a nested inventory, helping teams find an affected library instead of searching blindly. Dependency pinning and lock files keep builds on reviewed versions rather than silently accepting every release. Code signing shows which identity approved an artifact, while access controls and multi-factor authentication reduce the chance that one stolen password can publish it. Reproducible builds let independent systems check whether the same source and inputs produce the same output. Protected build environments, short-lived credentials, peer review, and separation of duties make tampering harder. Continuous monitoring watches for new advisories, unexpected package changes, suspicious builds, and misplaced secrets. None of these controls is complete. An inventory can be wrong. A pinned version can preserve a vulnerability. A valid signature proves who signed something, not that the code is safe. Reproducibility cannot protect deliberately malicious source. Monitoring usually begins after a signal exists. Controls also add friction. Teams are judged on speed, uptime, and features. Deep verification costs time, expertise, and money. The practical answer is to identify critical dependencies, reduce unnecessary ones, fund maintainers, isolate builds, demand stronger evidence for high-impact components, and revoke trust quickly. Modern software is not a single product. It is a network of trust relationships among developers, maintainers, vendors, machines, credentials, and update channels. Security comes from making those relationships visible, limited, and continuously questioned. Subscribe to Critical Failure for more investigations into the hidden systems shaping the digital world.